All right, guys, so we are moving on to target 2. You'll notice that we're still with the graphs of the polar equations and everything, but now we are finding the points of intersection between the two polar graphs. This ends up having a lot of different calculus applications. I'll kind of talk about that a little bit as we go through them. We're not going to necessarily, do the calculus applications, but it is going to have a bearing on what you guys are going to be doing in there next year. So taking a look at this, you'll notice that I already filled in all of the graphs on here. Honestly, that was just to save us a little bit of time so you don't have to listen to me, talking through everything the whole time. So what you might be a good idea to do, we do have a quiz on the graphs on Wednesday of this week. So it might be a good idea to pause the video, go through, practice all of these graphs. Again, they can just be sketches of them. It doesn't have to be 100% perfect here right now, but it might be a good idea to go through and sketch all of the graphs. Again, I already just drew them in, so you can take a look at them and go through that way. But again, what's going to end up happening here is you're going to want to see these systems really graphically and algebraically. And there's really a couple reasons for that. Really, once you get to calculus, it's a thing where it's basically one of our rules in calc that graphs are not sufficient in basically proving and justifying a solution to a system. It's just one of those things. You have to have the algebraic part of it. However, the graphs are actually very, very helpful because sometimes you'll see that our algebraic methods may not necessarily give you all of the solutions. So you might want to compare it back to the graph just so you can see it visually. So that's why we're going to have you do both of them, again, just to kind of prep you for that part of it. Again, the graph, really, when you get to calc, you won't get credit for just showing graphically how you solved a system. You have to show the algebraic as well, but again, it gives you that sort of visual to see. So we're going to be doing both on there. So that's my spiel on that part of it here. So again, and if you look at number 1, I already did the graphic part of here. So really, you can see that there's going to really just end up being probably one solution. You might be able to tell where that solution is, but let's see how we can do that graphic or algebraically here. So really, it's kind of how we solved things before. So if I have r equals to 3 and r equals 3 sine of 3, if they both equal r, they would both equal each other. So 3 is equal to 3 sine of theta, which means we really want to know where is the sine of theta equal to 1, and we know that the sine of theta is 1 at pi over 2. Again, you can kind of see that already on our graph. Both of these points right here are along the pi over 2. Both of these are kind of some of our simpler polar graphs. Both of them are our circles. You can kind of visually see that really it's at that theta is pi over 2. When we write our answer, we are going to use, and I know it seems kind of weird, we're going to use the word at theta equals pi over 2 is actually how we write it. Part of the reason here is we aren't even going to go through and find our R value. We're not going to write it as an ordered pair. I mean, we can see what our R value would look like on here, but that's actually not even a big part of this here. When you're doing calculus, what you're going to be doing is you're going to be finding the area between your different curves here. For example, okay, if I said, let's find the area on the inside of the circle r equals 3, but on the outside of the circle r equals 3 sine of theta, just in quadrant 1. So what I mean by that, just visually, in calculus, you're going to be finding, for example, this area along the inside here. What you do with that, it's actually called the integral. Okay, some of you may have heard of the integral before. That's the area between curves or under a curve and so forth along the way. Maybe you've seen the symbol like this, and like at the bottom here and at the top here, again, if you've seen any of that, there's usually what those are called are the bounds of our integral. In these scenarios, those bounds really are the theta values. Okay, those are going to end up being the theta. So really that's what's the most important thing here is finding out at which theta values, where do they intersect there, because that's going to be kind of the whole point when you go through and look at those integrals on there. So that's kind of part of what we are just kind of prepping you for. That's why, like I said, we're going to be writing our answers really kind of like that. Just the at theta equals, in this case, just pi over 2. So that one was one of ours, maybe a little bit simpler ones, hopefully. Looking at number 2, we've got r equals sine of theta. That is my blue circle. And then r equals 1 plus the cosine of theta. That's my cardioid, the orange cardioid here. So when we look at this, again, we can kind of, again, maybe see how many times these intersect each other. However, it might be a little bit harder to tell exactly where it is. Like, you know, maybe here and here, but especially that point at the pole there, that's where it might be a little bit more difficult to see. So let's actually go through and solve this one algebraically here. So if r equals the sine of theta and r equals 1 plus the cosine of theta, we can set them equal to each other. So sine of theta equals 1 plus the cosine of theta. We've actually solved this. You may not totally remember this. It was actually in class before we were out of class and everything. Typically what we did was we subtracted that cosine over, and then we squared both sides. Remember, part of the reason it was helpful to square both sides there was now we can get some sine squareds and cosine squareds along the way. So if we square both sides, we get this so far here. Oops, sorry, plus cosine squared when we square that, and that equals 1 on the other side. The reason that this is helpful, sine squared plus cosine squared is 1. So we get 1 minus 2 times the sine times the cosine, and that's equal 1. If we subtract the 1 and divide by -2, really you get sine times the cosine is equal to 0. So that means we want to know, where is the sine 0 and where is the cosine 0. So the sine is 0, we know, at 0 and pi. The cosine is 0 at pi over 2 and 3 pi over 2. Now, that gives us four places where they intersect. However, we can see from our graph, there are only 2 places where it intersects. If you remember back to when we squared things, a lot of times we did get some of those extraneous solutions along the way. That's kind of part of what we're looking at here. There's some extraneous solutions. So it's our job to kind of go back and look at the graph. This is where our graph makes it a lot more helpful along the way here. So if I look at this, if I'm going to trace along here, let me get a different color here. If I think about, let's do first r equals 1 times the cosine of theta on that. If I were to plug in 0 on this, because this, a lot of people mistake that point at the pole right here to always be 0, 0. What's kind of tough at this on these polar graphs here is that polar graphs really can have multiple ordered pairs that match the same point. That's different from our Cartesian coordinates, right? Cartesian coordinates, it always has one ordered pair. That's the only ordered pair. But really, this point, especially at the pole, can have multiple ones. Even this point, over here can have different ones depending on if we think r is positive or r is negative along the way. So that's one thing you have to be kind of careful with here. So if we're thinking about it, if I were to like trace along this graph, if I were to put in theta is 0, along this graph, the r equals 1 cosine theta here. If I were to put in theta is 0, cosine of 0 is 1, 1 plus 1 is 2. You'll notice, I didn't even say this in the beginning, we scaled this graph, so out here is 2, and then right here would be 1, just to make it a little bit bigger and easier for you to see. So out here is 2. That's where we actually start. So then we curve around and we follow along, and right here at pi over 2, that is going to be one of our solutions right here, and we'll talk about that. So right here is where theta is pi over 2, and then it's going to curve around and come right here, and it's actually at where theta is pi where it's 0. If I were to put in the cosine of pi, that's -1. 1 plus -1, that's where we get 0. Then I'm going to curve back around. Here's where theta is 3 pi over 2, and curve back around to kind of come around back to where we started here. If I'm looking at the circle, just the r equals sine of theta there, at 0, sine of 0 is 0. But again, that was a different place than where we were at 0 for the cardioid there. Then we're going to make our way around, and we know at pi over 2, it's going to be up here at 1. At pi, it's going to be back to 0. So that's one way that we can tell that our solutions are actually pi and pi over 2, not 0 and 3 pi over 2. Again, kind of going back and thinking about it there, it wasn't at 0 for this one, the r equals 1 cosine theta right there. It was actually at pi. So again, right here, if you go back and think like r equals the sine of pi, that would be where r is 0 on that one. And then here r equals 1 plus the cosine of pi. R would equal 1 plus negative 1 or 0. So that's going to be that intersection point. So our two solutions, I'm going to say at theta equals pi and theta equals pi over 2 for those. Okay, let's keep going here. So for number 3 here, so you'll notice that this one is a circle. The reason we put this on here is just to give you an approximate way to graph that circle. Again, the graph is more of a visual to see how many places does it intersect, how many solutions should we end up having. You can kind of tell that there should be 1, 2, 3, 4 solutions. Now again, our graph isn't perfect here, so it's not going to be exact on here, not an exact way to prove it. But let's show those 4 solutions algebraically here. So if r is 3 over the square root of 2 and r squared is equal to this, we can put that r in, because then we're saying, okay, that r has to be 3 over root 2. So we square it, and this gives us 9 halves is 9 times the cosine of 2 theta. This is where all of our solving work that we were working on came in handy from our last unit here. So really, if you remember from any of that, again, we want to have our interval now to 4 pi, so we need to find all of our solutions here. So the cosine is 1/2 at pi over 3 and 5 pi over 3, but because we need to go all the way to 4 pi, I'm going to have to include 7 pi over 3 and 11 pi over 3. So when we divide by 2, I get pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. I'm going to put, again, my at there to show us that that is where it is intersecting. And again, you can kind of see it's not a perfect graph here, but you can see those would be our 4 points of intersection. That one's a little bit more straightforward. All right, let's try some of them on the back. Some of them on the back are not quite as straightforward. Doesn't necessarily mean that they're a lot harder here, but not quite as straightforward along the way. So if you look at these two, these are both our cardioids here, orange and blue. We got nice Illini colors here. So as we go through these here, the one in blue is our first equation here, and the one in orange is our second one here. Okay, so you can kind of tell just by looking at it that there should be 3 points of intersection. Now, what's going to be weird about this one, when we solve this equation, so if these both equal to r, that means they both could equal each other. When we solve it, we're actually only going to get 2 solutions. So I'll show you here. We'll subtract the 3 from both sides, add the 3 cosine of theta over, so we end up getting 6 cosine of theta is 0. If we divide by 6, really we just want to know where is the cosine 0, and that is at pi over 2 and 3 pi over 2. Now we can see that that does actually correspond to 2 of those points. We have at pi over 2 up here and at 3 pi over 2 down here. So that gives us 2 of them. But what about that point in the middle at the pole? That's going to be something that's a little bit different that we have to think. And that's why our graphs are so important. This kind of illustrates our need to have to do it graphically and algebraically here. So this one's going to be a little bit unique, because you're going to see that it's actually at different theta values for each of the graphs where it hits the pole, but we still count it as an intersection point here. So what I mean by this, if I'm looking at the graph in blue, we basically want to know where is R 0. So R is 0. If I were to go kind of quickly through this here, I would subtract the 3, divide by 3. We want to know where is the cosine -1, and that would be at pi. So if I were to follow along my blue graph, if I put in theta is 0, I would get 3 times 1 plus 3. I'd be out here at 6. And then I'm following along. I'm kind of tracing on the outside just so you can see what happens here. Here I'm at pi over 2. Okay, and then if I keep coming around, at pi is where it crosses through the pole right there. Okay, that's what that's saying. Then again, we trace it back around here. This is 3 pi over 2 where they intersect, and then it comes back around. Now, if I look at the graph in orange, again, if we want to know still where R is 0, that's where it crosses through the pole. Subtract the 3, divide by -3. We're solving where cosine is -1. That is at at +1, that is at 0 here. So again, here, for this one, the graph, if I were to put in 0 for the orange cardioid here, it starts at 0, then goes to pi over 2 and crosses through, and at pi, if you plug in pi into our equation here, we're actually going to get we're going to get 6 here, but it's going to be in that opposite direction there. So that's one thing you have to kind of be careful with. And then it keeps, coming around and then comes back around to the pole there at 2 pi. So this one you actually have to say a little bit differently here. And again, this is why it's important when you get to calculus, because when you get to calculus, again, you don't have to do this right now. For example, though, we might be finding like the area in here that I just shaded in green. And the nice thing about it is the top half and the bottom half are the same. So it's symmetrical. You would actually eventually end up being able to just kind of, do one of them and then, double it for the bottom part as well when we're finding the area. But you really need to be able to know where those theta values is so you can create your integral. So the way that we answer this, we actually have to say kind of really a different thing. You have to kind of say that along one of the graphs. So you have to pick one. So say I picked along 3 cosine theta plus 3. They intersect. That's the word at. Sorry. Oh my goodness. Hold on. Let me get back to it. There we go. Sorry, guys, technical difficulties here. At theta is, so again, it started at over here at 0. It was at 6. Then it came around at pi over 2. And then at pi and 3 pi over 2. That says over 2 here. And that, again, really actually could be your answer. However, you could have picked the other one. You actually don't need, my goodness, my internet I think is just going really, really slow here. It's delaying here. So you could say along R equals 3 minus 3 cosine of theta. Oh my goodness here. You could say at the different points on here. So at theta is, this one would be theta is 0 pi over 2. And 3 pi over 2. Let me pause this and see if my internet comes back here. Okay, I gave it a little rest. Let's see. Again, my writing has been really kind of crazy here. So anyways, coming back to it, again, you really actually only need to say one of them along the way here. So you pick one along the R equals, the first cardioid or the second cardioid. But again, really that's showing that it's the same location on the graph, but it's at a different theta value. And again, that's going to be important when you set up your integrals eventually next year. All right, let's try another one. If I look at number 5 here. So this is going to be another one that's, again, a little bit different to think through. You can see along the way here that there are 1, 2, 3 points of intersection that we're looking for. So let's quickly solve this. So they both equal R. So 1 equals 2 sine theta plus 1. Subtract divide by 2. So we want to know where is the sign 0, and that is at 0 and pi. So you can tell that gives us two of them. That gives us here at 0 and here at pi. So we've got that one. But it didn't give us the third value here. Really, again, when you think about it here, if I'm going around my, let me use a different color. I'm going to use pink here. If I'm going around the limacon that has that inner loop there, if so that's this graph right here, r equals 2 sine theta plus 1. If I put in 0, my first value is 1. This is where the graph starts. It comes around at pi over 2. It's up here. It's way up here. Again, this is scaled to 3, so it'd be up here at 3. Comes back around at pi is our other place it intersects. Then it comes and goes through the pole. I think it's at 7 pi over 6 it goes through the pole. Then it curves back around, and right here we're at 3 pi over 2. At 3 pi over 2, if I were to plug that into this equation here, sine of 3 pi over 2 is -1. We get -2 plus 1, or -1. So that's where it actually intersects, then comes back around through the pole, and then comes back to where we started. If I'm looking at my circle, though, at 0, it would be here, and then it curves around pi over 2. It's up here at +1. So again, it's that same spot where those two intersect, but it's along two different things. So once again, we have to write our kind of one of these here. So let's say if I'm doing along r equals 2 sine of theta plus 1. Think about where that would be. So that's at theta is still at 0. That points straight forward. And then along this one, it was not at pi over 2. At pi over 2, the limacon was up here at 3. So then it's actually at pi and at 3 pi over 2. Again, at 3 pi over 2, the value for that limacon was -1. That's where it intersects. And this could be your solution. You could choose. Again, you actually only need to do one of these. I like to write them both down just so you can check them, so you can pick one. So if you were doing it r equals 1, that's at 0, pi over 2, and, pi, I meant to write here, and at pi. Okay, so that's a couple examples of where the graph really, really helps you out there. All right, last one here. This one, again, is going to be something you really have to think about with that rows. So r equals 2, our circle, and then here is where you have to think about how our rows is graphed. When you think about this, again, that r value is really how far away it is from the pole. So when we actually went and solved this, like if I were to find the ends of the petal, if I were to graph it using the ends of the petal, we would want to solve where it's 4 and where it is -4. Okay, again, if you were to only solve where r was 4, you would actually only get these 2 points. Where r is -4, you would get the other 2 petals. So you need to think really when you're doing those that the r value, when you're going all the way around your circle, it could actually be positive or negative along the way there. Okay, so with that said, we need to think, okay, if I want to know where r equals 2 intersects, you can tell that there's 1, 2, 3, 4, 5, 6, 7, 8 places where they intersect. If you were to only solve for r as +2, you'd be missing out on half of our solutions. So you actually want to solve for positive or -2 here. That's a cosine. Sorry, again, it keeps getting kind of delayed when I write, and then it gets all slappy here. So positive or -1/2 here. So I'm going to go kind of quick through this here. Again, thinking where the cosine is 1/2, that'd be at pi over 3, 2 pi, and -1/2 as well, 2 pi over 3, 4 pi over 3, and 5 pi over 3. But we need to go all the way to 4 pi. Again, for our interval, it would be We'd have to double everything here. So add 2 pi to everything, take one more loop around. So we get 7 pi over 3, 8 pi over 3, 10 pi over 3, and 11 pi over 3. So when we solve for it, I'm going to write my at in here already. We're going to have at theta is pi over 6. That ends up reducing, sorry, to pi over 3. And then here we get 2 pi over 3. Goodness. We All right, I need to stop, don't I? Struggling here. Okay. At 5 pi over 6, at 7 pi over 6. If I reduce this one, that's 4 pi over 3, 5 pi over 3, and 11 pi over 6. Sorry, it is especially sloppy along the way there, but you get the idea. And that gives us all 8 of our solutions there. All right, you've got 4 of these for your work here. I want you to try all 4 of them because some of those are some special cases there that I want you to practice. They're all a little bit different. Again, best thing about it is you can graph and sketch and practice all of those graphs for your quiz on Wednesday. If you're feeling pretty good about that, you can go quicker through the graphs. I'm okay with that, but I still want you to do the graphic part and the algebraic part so that way you can kind of check yourself. All right, as always, let me know if there's questions and have a great day. Bye, guys.